40 Days of Chemistry Part 11. This time looking at the second part of 9.3.4, looking at standard solutions and titrations. And the first thing is standard solutions. You should know what a standard solution is by now. And one of the key aspects they're going to ask questions about is choosing chemicals for a standard. And the main ideas are the chemical you must choose for a standard must be soluble, it's got to dissolve in the solution, it's got to be high purity so it's accurate, it's got to have a precisely known formula so you can find out a number of moles, a high molecular weight is preferred to reduce weighing errors, and one of the key ideas is that it must be stable in air. So that's one of the reasons you can't use sodium hydroxide to make a standard. It absorbs water, it reacts with carbon dioxide, therefore its accurate mass cannot be measured precisely, so you can't use sodium hydroxide to make a standard. So what do you do to make a standard solution? You should know the steps for making a standard solution. We've done it twice, Year 11 and Year 12, and there's the key steps there. If you're not sure, just pause the video and have a look at them to make sure you understand the key steps. The next thing is the titration. Once you've made your standard, you can do your titration. You should be able to define a titration. You need to know that you use volumetric flasks, burettes, and volumetric pipettes because they allow for accurate measurements, and the whole point of a titration is to make accurate measurements. The cleaning steps are critical as well. The pipette and burette, they're cleaned with water, distilled water to remove any impurities, and then they're cleaned with a solution that's actually being added to them to avoid dilution of that solution. So once you rinse it out with water, you then rinse it out with that solution, so you've got a residue of that solution on the inside, which won't dilute the solution when you add it. The conical flask, though, which the reaction takes place in, the reaction flask, is clean with water only. And the reason for that is that we use the pipette, that volumetric pipette is used to measure an exact volume of our solution into the conical flask. If we'd clean the conical flask with the solution, we'd have a residue of that solution on the inside of the flask, and therefore we'd have too much volume or too many moles of that solution inside our conical flask. So we only rinse with water to ensure the exact volume or exact number of moles are being transferred from the pipette. Indicator selection is a key concept when we're looking at titrations. You need to know that the point at which the stoichiometric ratio of reactants has been added, that's called the equivalence point, where the acid has just exactly neutralized the base, and that point can be determined by using an indicator. The indicator must be chosen so that its color change or endpoint matches the equivalence point, and hopefully you're going to spell equivalence point correctly. Now you know that acid plus base goes to salt plus water, and therefore the pH of the salt determines the pH of the equivalence point, and there's more details on that in episode 9 of this series. We know that a strong acid and a strong base turns into a neutral salt, and therefore you want an indicator that's going to change colour around pH 7, and the indicators we use are that bromoethanol blue, which changes from yellow to green to blue at 6.2 to 7.6. You can lose litmus though, which changes from red to purple to blue at 6 to 8. If you've got a strong acid, weak base titration, you're going to get an acidic salt at the equivalence point, which means the endpoint equivalence point will be slightly acidic, and therefore you want to use methyl orange indicator. It changes from red to orange to yellow at 3.1 to 4.4 pH. And lastly, if you're using a weak acid and strong base, you're going to get a basic salt produced, so the equivalence point and endpoint need to be in a basic solution, and use phenolphthalein as an indicator. It changes colour from clear to light pink to crimson at 8.3 to 10. Once you've chosen your indicator and everything's sorted out, then you undertake the procedure for a titration. You've done titrations many times, you've written the method up a number of times, the steps are there, or the key steps are there to remind you of what to do. One thing you might want to make sure you can actually draw these 4 bits of apparatus. You need to be able to draw burettes, conical flasks, pipettes, and volumetric flasks. One titration you have to do in the HSC course is computer-assisted titration, and you do a computer-assisted titration to develop a pH curve, which is a graph of pH versus the volume of one of the reactants you're adding. In this case, this graph here is from a HSC question. It's graphing pH versus the volume of base added. Now, the advantage of using a computer-assisted titration and making a pH curve is, once you've got a pH curve, you can actually analyse weak acid, weak base titrations, which can't be done with an indicator. And second of all, it removes human error from judging the endpoint, because you're allowed to overshoot the endpoint in these sort of titrations. It doesn't matter how much excess acid or base you add, because once you've got the curve, you can actually figure out the endpoint and equivalence point from the curve. You don't have to worry about the colour change of indicator and human error in judging the exact endpoint. Now this is a situation where we've got 2 different curves, and one of these is strong acid, strong base titration. That's this one here. You can tell it's a strong acid, strong base titration for 2 reasons. First of all, it starts off at a fairly low pH and finishes at a high pH, so obviously you're adding base. And second of all, we look at the actual endpoint or equivalence point. Now, when you have a titration curve, the inflection point is where the equivalence point is. Now, what the inflection point means, if we look at this line here, this has got a slope And as we get closer and closer to the equivalence point, the slope starts to increase. It's getting steeper and steeper and steeper. The inflection point is the point at which it stops getting steeper and steeper, and the curve starts getting less steep again. So that inflection point is that point right in the middle there, and you can see that the end point or equivalence point of this titration is about pH 7. And we know that when you've got pH 7, that means it's a strong acid, strong base titration. We've got a neutral end point. This curve here, its equivalence point is up here at pH 9. It's got a basic end point, and therefore it must be a weak acid reacting with a strong base. Now, we note though that the volume of base required for both these titrations is different. This strong acid required, say, what's this, 25 mils or 24 mils of base to neutralize, whereas the weak acid required about 37 mils to neutralize. And that suggests that even though this is a weaker acid, it was at higher concentration because it required more base to neutralize it. Now what I've got here is a similar sort of curve. I've still got the strong acid, strong base curve and the weak acid, strong base curve. And I've put 3 extra curves on. I've got this orange curve here, I've got a blue curve, and there is a green curve. What you should do is pause the video and see if you can figure out, first of all, what sort of titration is taking place. Is it strong acid, strong base, weak acid, weak base? And what sort of concentrations are they dilute or concentrated solutions we're adding? So have a pause, have a think about it, and then we'll go over the answers in just a second. Okay, let's have a look at this first curve. One thing to note about this first curve, it starts off with a low pH and finishes at a higher pH. So obviously it's starting with an acidic solution and we're adding some sort of base. But the one thing to notice about this curve is that it's doesn't have a very sharp transition. Most titrations have a sharp transition where the pH changes very, very, very quickly. This one's got a fairly smooth transition. The inflection point or equivalence point is around pH 7. So what this suggests is it's a weak acid, weak base titration. There's no sharp pH change. We do end up with an equivalence point about pH 7, and this is the sort of curve that you can only use titration curves or computer-assisted titrations to figure out. You couldn't use an indicator here because it hasn't got a steep curve. So that's a weak acid, weak base titration. Look at this second example, number 2. We're starting off with an acidic solution, we're adding base, and we end up with a slightly basic solution. Look at the equivalence point though. The equivalence point's down here around pH 5, which is an acidic solution. The fact that the equivalence point's an acidic solution suggests this is a strong acid, weak base titration. And it's the same for this example number 3. Once again, the equivalence point is down here, this time around pH 4. So once again, it's an acidic equivalence point, which suggests it's a strong acid, weak base titration. But notice that this titration here only required 12 mils of base, and this one here required, say, what's that, 33 mils of base. So you can draw a few conclusions here. First of all, this one didn't require much base at all to neutralize. Either the acid itself was very dilute, or this base could have been quite concentrated. This blue curve here in the curve number 2, it took quite a lot of base to neutralize, suggesting that the acid was either concentrated or the base was dilute. Whenever doing calculations or asked to do calculations on titration, there are a few usual steps you've got to follow through. First of all, make sure you write your proper balanced chemical reaction equation to get the proper mole ratio. You can find the moles of the standard in any titration because you know the concentration of the standard already, and the standard will either be inside the conical flask, so it's been measured with the pipette, or it's been measured with the burette, and therefore you'll always have the volume of the standard as well. So once you know the concentration and volume of the standard, you can find the moles of the standard. Now once you know the moles of the standard, you can use your balanced equation to find the moles of the unknown. So now you know the moles of the standard, you also know the moles of the unknown. And once you know the moles of the unknown, you obviously also know the volume of the unknown, because that's part of the titration. Whether the unknown was in your conical flask or the burette, you know the volume. So once you know the number of moles and the volume, you can find that concentration of the unknown. Now there's 2 common tricks they give you in titration sort of questions in the HSC. The first of all, because you run titrations a number of times to get some very close values, they'll often give you a table of results for titrations. One of those values will be an outlier. So make sure you look for that outlier and you exclude that outlier from your calculations. The second trick is giving you some reactions that involve polyprotic acids. For example, citric acid, even though it's weak, it'll still neutralize 3 times as much sodium hydroxide as hydrochloric acid will, because strong bases cause acids, whether they're weak or strong, to give up all their protons or protons they can donate, and therefore just be aware that citric acid, being triprotic, can neutralize 3 times as much sodium hydroxide as hydrochloric acid can, because hydrochloric acid is monoprotic.